So, dear students, welcome back to our NPTEL online certification course on analog electronic circuit. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. Today's topic of discussion, it is continuation of differential amplifier. In the previous lecture we have completed analysis, and today we will be talking about numerical examples. The concepts we are planning to cover, it is the following. As I said that the analysis part, it is done in the previous two lectures, and we are going to talk about numerical examples, and we do have primarily differential amplifier using BJT. Then we do have differential amplifier using MOSFET, and then also we do have another example where we do have the differential amplifier. We do have both types of transistor, MOSFET as well as BJT. So, this differential amplifier having the BJTs, it will be having different perspective, namely the DC operating point, and then small signal parameters, then differential mode gain, common mode gain, and then going to the input range and output swing. So, almost every aspects it will be covered with this example. Similarly, here also will be covering most of the aspects, and then in the third example we shall try to see that how the performance can be enhanced by replacing one of the passive element, namely the tail resistor, by active device to enhance the performance. Okay. So, we do have differential amplifier realized by BJT. So, this is the circuit we have discussed before, and you may recall that in our most of our analysis we used to split this resistor RT into two identical elements in parallel, and the intention of that was to get more insight of the circuit, particularly to see how the differential signal and common mode signal, they are getting propagated from primary input port to the primary output port. Now, but then actual circuit, of course, we do have only one tail resistor. So, the analysis we have done there where this RT it was split into two identical part, and then if you connect the emitter of the two transistors together, then this circuit and that circuit, they are essentially same. So, in our discussion now, most of the time we will be using this tail resistor, it is connected together. So, here we do have the different device parameters, namely for BJTs we do have beta. In this case, this beta may not be having much of use, but for the sake of completeness we are keeping the parameter. And then we do have the VBE on of both the transistors 0.6. In fact, we are considering Q1 and Q2, they are identical. And then we also have the early voltage of the two transistors equals to 100 volt. And then we do have the supply voltage equals to 12 volt. And then the loads RC1 and RC2 both are equal, and they are equal to 5.2 kilo ohm, and the tail resistor it is 1 kilo ohm. Then load capacitance, for this example it is not mandatory, but just to say that we may consider high frequency signal also, and then we can consider that the load is also balanced, namely the load here CL1 and CL2, they are in this case they are both are equal to 100 picofarad. Now, to start with, we do have this DC voltage given to us, which is 2.6. In fact, this DC voltage should be sufficiently high, so that Q1 and Q2 should be in active region, and on the other hand, this DC voltage should not be too high, otherwise Q1 and Q2 may enter into saturation region. So, here we have picked up the value of this DC voltage well within its range, allowable range. So, with this 2.6 of V in C, let us try to find the operating point of the transistors, and of course, we have considered Q1 and Q2, they are identical. So, how do you proceed? First of all, for DC analysis, we can ignore the AC signal part, and then we may say that we do have 2.6 volt here and also 2.6 volt here at both the base terminal of Q1 and Q2. Now, if I consider VBE on drop of 0.6, then we do have the emitter voltage DC wise, it is 2 volt. Now, RT equals to 1 kilo ohm. So, the current flow here it is 2 divided by 1 k. So, that is 2 milliampere. And under quiescent condition, in absence of the small signal, this 2 milliampere current it is equally getting divided into 2 halves, one for the left branch and another one is for the right branch. So, 1 milliampere current it is flowing through Q1, likewise for the Q2. Now, we assume that of course, this is the emitter current 1 milliampere. So, we assume that the base current is very small. So, we can say that the collector current of transistor 1 as well as transistor 2, both of them we can well approximate by 1 milliampere. Now, we do have 6 volt here, sorry, we do have 2.6 volt here, we do have 2 volt here, and now we do have 1 milliampere current is flowing through this resistor, which is having a value of 5.2 kilo ohm. So, the drop across this resistor it is 5.2 volt. So, the voltage at the collector, DC voltage at the collector it is 12 volt minus 5.2. So, that is equal to 6.8. So, we can say that now we obtain the operating point and then also we obtain the DC voltage. DC voltage it is same here also 6.8 volt. Okay. So, to summarize the DC operating point, we do have 2.6 volt is the base voltage, and then at the emitter. So, here also it is 2.6 volt, and at the emitter we do have 2 volt, and then voltage here it is 6.8 volt, and here also it is 6.8 volt, and the collector current in both the transistors they are equal and they are 1 milliampere, right. So, that gives us the operating point of both the devices. In fact, you can calculate what is the VCE and ensure that Q1 and Q2 both are in active region of operation. In fact, we do have sufficient headroom. So, in case if you have say VCE set is 0.3 volt. So, this voltage it can come down as low as 2. So, this voltage it can go as low as 2.3. So, likewise, so we do have a swing here with respect to DC voltage, it is 6.8 minus 2.3. So, that is equal to 4.5. So, the negative side swing it is 4.5. So, the output swing, so negative side it is 6.8 minus 2.3 volt, right. So, that is considering VC voltage, it is equal to 0.3 and that is equal to 4.5 volt. So, likewise for positive side, the voltage here it can go towards the supply voltage. So, here we do have 12 volt DC and then the DC voltage at the output it is 6.8. So, the positive side on the other hand it is 12 minus 6.8. So, that is equal to 5.2 volt. So, we do have fairly good swing. So, which means that whatever the DC voltage we do have, over that DC voltage we can have very nice signal swing. So, the circuit operating point it is very good. So, 6.8 volt is the DC level. So, now we obtain the output swing. So, we obtain operating point, we obtain the DC voltage. Now, next thing is the small signal parameter of transistors. So, we do have the collector current I c equals to 1 milliampere and that gives us G m equals to 1 milliampere divided by 26 millivolt. If I consider thermal equivalent voltage, it is 26 millivolt. So, that is equal to 1 by 26 mho, and then R pi equals to beta divided by G m 1. So, that is 100 multiplied by 26. So, that is equal to 2.6 kilo ohm, and then output resistance R O. So, that is equal to early voltage divided by I c. So, this is equal to 100 divided by 1 milli. So, that is giving us 100 kilo ohm. So, we assume that this 100 kilo ohm it is much higher than this passive load R c 1 and R c 2. So, that gives us the small signal parameter. In fact, for the other transistor parameters are also same corresponding to whatever the parameter we obtain for Q 1. So, now we obtain the small signal parameters of both the transistors. Next thing is we need to find the small signal gain, namely the differential mode gain and common mode gain. So, the differential mode gain A d equals to G m into R c, and this is equal to R c it is 5.2 and G m is equal to 1 by 26, and this is of course, it is kilo ohm. So, into 10 to the power 3. So, that is equal to 200, and the common mode gain on the other hand it is G m into R c divided by 1 plus G m into 2 R t, right. And so, in the numerator we do have 200, just now we have calculated, and then we do have 1 plus 2000 divided by 26. So, so this is equal to how much? 2000 divided by 26. I do have a calculator for me. So, 2000 divided by 26 is equal to 77 plus 1 in the denominator, and so that reciprocal of that multiplied by 200 is giving me 2.566 and so on. So, in fact, if you ignore this 1, you will be getting this is equal to 2.6. Of course, it is having a minus sign, right. So, we do have the differential mode gain of 200, and then we do have the common mode gain. Common mode gain is basically approximately it is minus 2.6. So, now next thing is that once we feed the signal, once we feed the small signal, namely V in 1 and then V in 2, based on this differential mode gain and common mode gain, we will be getting the signal at this point, namely at VO2 and then VO1. And to get the individual signal, first of all, based on this AD and AC, as we have done for the macro model based numerical example, to get the individual signal, first thing is that we need to see what is the differential input, and then what is the common mode input, and then we multiply this differential and common mode component of the input by their respective gain to get the VOD and VOC, and from that we can find what will be the individual signal. So, keeping the operating point same, let we find what will be the corresponding output for a given set of V in 1 and V in 2. So, in the next slide what we have, it is so we are keeping the operating point same, namely we do have V in C equals to 2.6. So, this is equal to 2.6 volt, and that gives the whatever the operating point we obtain, and we know that DC voltage wise VO DC equals to so that is 12 minus 5.2. So, that is 6.8, right, and also we have calculated the AD equals to 200 and AC on the other hand it is minus 2.6. Now, here we do have the V in 1 and V in 2, and if you see here this part similar to our numerical examples associated with the macro model, V in, so this 2 if I consider, so this is giving us V in D equals to, so V in D equals to V in 1 minus V in 2. So, that is equal to 0.02 sin 2 pi by capital T into small t. On the other hand, if I consider the common part, namely if I take the average of the two inputs, so that gives us the common mode input V in C. So, that is equal to V in 1 plus V in 2 divided by 2, and that is equal to 0.2 sin 2 pi by 4 t into t. So, we do have the common mode component and we do have the differential mode component here, and we do have the differential mode gain and common mode gain. So, from that we can get VOD equals to so this 200 multiplied by 0.02. So, that gives us 200 multiplied by 0.02 sine 2 pi by capital T into small t. So, that is equal to 4 sine 2 pi by capital T into small t. So, that is the differential output. So, likewise we can calculate the common mode output. VOC equals to minus 2.6 into this common mode part 0.2 into sine 2 pi by 4 t. It is having different frequency. So, this is equal to how much? This is 0.52 sine 2 pi by 4 t into small t, of course, with a minus sign. So, now we have obtained the differential and common mode component. So, the individual signal, now we can say that, say VO1, it is having the DC part 6.8 volt DC, and then we do have the common mode part. So, that is minus 0.52 sine 2 pi by 4 capital T small t, and then it is also having half of the differential part. So, that is equal to plus 2 sine 2 pi by capital T into small t. So, likewise, if you see the other output VO2, so that is also having DC of 6.8, and then the common mode part minus 0.52 sine 2 pi by 4 t into small t, and then minus 2 sine 2 pi by capital T into small t. So, that gives us the complete output. So, we can see here this is the common mode part. So, this part and this part they are common mode, and then we do have the differential part here and here. And if you compare the common mode part and differential part, it is almost that differential part, if I see individual signal wise, and if you take particularly the differential output, differential part, it is quite large, in fact almost 8 times higher. So, this part it is almost 8 times higher than the common mode part. However, if you see at the input, if you compare the differential part, which is 0.2 and then common 0.02 rather, and common mode part it is 0.2. So, here on the other hand, the common mode part it was 10 times higher, which indicates that whatever the signal we are receiving here, that may be getting affected by significantly I should say affected by unwanted signal having an amplitude which is 10 times higher than the desired signal, differential signal. And through this differential amplifier, which is having differential mode gain, it is much higher than the common mode gain, and that is why at the output we are getting the desired signal almost having 8 times higher amplitude than the unwanted component. The unwanted component is this common mode component, right. So, that is the basic motivation. Now, next thing is that how do we see the signal, particularly if I consider how the common mode and differential mode signal it is getting propagated. Particularly you may recall in the analysis we used to split this resistor into two parts, and we used to claim that this 2 RT and this 2 RT we used to split them, and then we used to see that the signal here and signal here it was propagating differently for common mode part and differential part. And now here at the input the stimulus it is having both differential as well as the common mode part. So, in case if you in this actual circuit if you split these two resistors, and we like to see what other things are happening, namely with this kind of signal what is the signal amplitude you are getting at the emitter and the output. So, again we are keeping the same operating point, only thing is that the RT it has been split into two parts, identical parts 2 RT, and also here we have opened it, here we have opened it. Now, in this case if we open it and if we are keeping the same stimulus, namely V in 1 and V in 2, then what happens? First of all, if you once you do have a split here, identical split here, and then even though we are applying the same 2.6 volt here, the operating point it is remaining same, but left and right half they are completely isolated. So, here again if you see the operating point, here the DC voltage it is 2.6, and the voltage coming here it is 2 volt, and now 2 RT having RT equals to 1 K, this current it is 1 milliampere. So, that gives us the emitter current 1 milliampere, and then the collector current is also very close to 1 milliampere. So, we can say that the and this 1 milliampere it is flowing through RC1, creating a drop of 5.2 volt, since its value it is 5.2 K. So, the voltage here again it is 6.8. So, with this split, of course, as expected the operating point is not getting changed. So, the corresponding small signal parameter, namely GM1 and GM2, they remain same, and both of them are equal to 1 by 26 mho, and R pi of the two resistors transistors, they are remaining 2.6 K, and then RO RO1 equals to RO2, they are equal to 100 K. Now, if I am having this parameter and then I do have a signal V in 1 coming here. So, what do we expect, that the left half it is completely isolated. So, just by analyzing this left part we can calculate what may be the signal coming here and the signal coming here. Okay. So, let me clear the board and then let me write those signals expression. So, the gain of this transistor Q1 and its corresponding associated bias, we can say that its voltage gain equals to GM1 into RC1 divided by 1 plus GM into 2 RT, of course, with a minus sign. So, what is the value? Here we have calculated this is equal to 200 and this is 1 plus close to 77 and this is equal to minus 2.56, or I should say approximately equal to minus 2.6. So, if I ignore this 1, then RC1 divided by 2 RT, that gives us 2.6. So, that is the gain from this point to this point, which means that for this input the output signal we are getting, namely VO2, what we are expecting here, it is minus 2.6 multiplied by V in 1, right. And then we do have two components, and if you see here, so the first component, it is minus 0.026 sin 2 pi by capital T into small t, and then we also have to multiply this 0.2 and 2.6 for this component. So, that is equal to minus 0.52 sin 2 pi by 4 t into t. You might have observed that since this circuit left part, it is completely isolated from the right part. So, this circuit, of course, it is working as common emitter amplifier having a degenerator of 2 RT. So, this circuit, of course, it cannot distinguish which is common mode part and the differential part. So, both the differential part as well as the common mode part, it will amplify, and whatever the signal it is coming here, it is given here. And also, if you see the signal at this point, so if I call that signal, it is V emitter 1. So, what kind of signal do I get? Before we consider this RT, we are getting almost the V in here, and then we do have the output impedance, which is 1 by GM1, and then we are connecting to RT. Note that this V in 1, it is not this V in 1, it is the signal coming at this point, which is very close to this signal, right. And so, before we consider this resistance, the signal here, if I consider it is having say infinite resistance, then at this point the signal, it will be same as whatever the signal we are applying here. So, that is why we are calling it as voltage, it is getting translated to emitter, or emitter is following the base terminal, and then we do have this resistance, which is 1 by GM1. So, once this Thevenin equivalent voltage source, it is getting loaded by 2 RT, then whatever the voltage we do get here, it is nothing but this RE1. So, this voltage, it is V in 1, the reflected signal coming to the emitter, multiplied by 2 RT, that is because divided by 2 RT plus 1 by GM1. That is because this signal it is getting divided across this 1 by GM1 and 2RT to create this voltage called VE1. So, this is the signal we are getting at this point. Before connecting the load it was like this, and then once we connect this 2RT, then whatever the voltage we are getting here. So, if I calculate this one, it is coming V in 1 multiplied by this is 2K. So, 2000, and this is 2000, this is 1 by GM1, that is 26. So, 2026. In fact, this part it becomes very close to 1. This is equal to 0.987. I think that was my calculation, 0.987 multiplied by this V in 1, which means that I do have this signal equals to minus. No, I do not have the minus sign here. I do have the signal coming in phase. So, I do have 0.01 multiplied by 0.987. So, I do have 0.00987 sine 2 pi by capital T into small t, and then we do have this part that is also getting multiplied by this one. So, that is equal to plus we do have 4791 point. So, this sine 2 pi by 4 t into small t. So, that is corresponding to this part. So, this is the signal coming at emitter here. In fact, similar kind of things you will be getting at the other side, namely at this point, and likewise here also you will be getting the signal. So, the signal coming here, it will be similar to whatever we obtain, namely the gain of this transistor along with its bias arrangement, it will be having the same gain of minus 2.6. So, we can say that VO1, this VO1 signal wise, it is equal to this is having minus, gain is minus 2.6, and this signal it is minus. So, I do have plus 0.026 sine 2 pi by capital T into small t, and then we do have this part. So, it is having a minus, and then we do have 0.52 sine 2 pi by 4 t into small t. So, we do have the two frequencies. Again, this amplifier it does not really understand the common mode part and differential part. So, both of these parts are getting amplified by the same gain. So, if I see individual signal, if I see the individual signal, this and this, of course, it is having both the frequency component, and if you are keeping this node still open, and if you consider the differential output, say VOD, which is VO1 minus VO2 by definition, And so, if I take the difference of this signal and this signal, then obviously, this part it is getting removed, leaving behind this part and this part multiplied by 2, because they do have opposite sign. So, what we are getting there, it is 0.052 sine 2 pi by capital T into small t, and this part, as I said, that they are getting removed. On the other hand, if I take the average of the two signal, so if I take average of this signal and this signal, that gives us the output common mode. And so, if I take average of VO1 and VO2, in fact, in that case this part and this part they are getting cancelled, leaving behind this part and this part. So, that is equal to minus 0.52 sine 2 pi by 4 t into small t. So, now if you see that this part, even if you are keeping this is open, the common mode part it is same as the case when we have connected it or in the previous circuit. But then the differential part, if you see, it is quite small. In fact, if you connect it to get the original circuit, then what we have obtained it is that corresponding differential output, it was having an amplitude, it was 4 volt, if you recall, right. And so, now if I make a connection, what we are expecting that the emitter voltage at this at the emitter of transistor 2, it is also having similar kind of signal, as you can see here, similar kind. So, what will be the difference? This part it will be same, but this part it will be having opposite sign. So, if I observe the voltage at this point before we make the connection, and we call this is say VE2. So, that is equal to this part, the first part it is having a minus sign, minus 0.00987, then whatever sine 2 pi by capital T into sine 2 pi by capital T into small t, and then this part on the other hand it will be having plus sign plus exactly this one 0.1974, then whatever it is. So, the moment we make this connection, this part and this part they are getting cancelled out, and also at the output this part and this part they got amplified, and both of them, this part it is getting converted into minus 2 sine 2 pi capital T into T with this connection. If you make this connection, same thing, this part is also getting increased to plus 2 sine 2 pi by capital T into small t, and naturally the amplitude of the differential part it got changed to 4 sine 2 pi capital T into T. So, this got changed to 2 and this is also 2. So, that gives us the amplitude of 4, right. So, in fact, in hardware you can make this experiment, namely you can construct this circuit, and then if you keep it open and then if you observe the signal here and here, what you will be seeing here, mostly the common mode signal it will be dominating, hardly you will be seeing the information out of the differential part, because at the input the strength of the differential signal is very small, and then the moment you make this connection, all of a sudden then you will see that the differential part, it will be appreciated, and then common mode component, however, it will be remaining same. So, in fact, you can do this experiment in lab setup, and you can get a feel of it, right. Okay. So, next thing is that we will see what will be the suitable range of this input common mode voltage, and so we have taken a meaningful voltage here, but we like to see what may be its meaningful range, namely lower limit and upper limit. But then let me take a short break and then we will come back.